Hi, in this lecture, we are going to talk about the vapor and combined power cycle. In this part, I'm going to talk about the ideal Rankine cycle. The outline of this part will consist of the vapor power cycle. I'm going to explain the reason why we cannot use Carnot power cycle with the vapor. And then I'm going to explain the details and the description of the nature of the Rankine power cycles. And lastly, I will conclude with several ways to improve the simple Rankine cycle efficiency. Now let's start with the vapor power cycles. The vapor power cycles means that the cycle which use working fluid which can undergo phase change. The fluid that we normally use would be water because it's abundant and it's very cheap. Abundant and it's very cheap. Moreover, water is non-toxic as well. Okay. So in the power cycle which use water or steam as the working fluid, it will consist of 4 pieces of equipment. The first one, it would be the pump that we use to increase the pressure of the liquid from point 1 to point 2. Okay. After that, the high pressure liquid will be used to absorb heat in the boiler, and it will change from the liquid into the vapor. Okay, and after that, the high pressure and high temperature vapor here will expand through a turbine, okay, where it can generate the work, okay, and exit at point 4. This is still vapor, but at a lower pressure. The vapor will be condensed in the condenser to return the vapor into the liquid and continue the loops at point number 1 again. So you can see that in this power cycle, the working fluid can change the phase in the boiler and in condenser. Okay, in the pump, the working fluid would be liquid, but in the turbine, the working fluid will be vapor. Now let's have a look at the Carnot vapor cycle using steam. The shape of the cycle on the TS diagram will be as shown here. You can see we have a red rectangle to represent the Carnot cycle. You have the black curve here to represent the phase boundary, okay, of the steam on TS diagram. You can see the area on the left hand side of the phase boundary will represent the liquid region. The area on the right hand side of the phase boundary will represent the vapor region. And lastly, the area under the phase boundary or the steam dome here will represent the vapor and liquid mixture region. Okay. You can see that we have 4 processes here in Carnot cycle, 2 isentropic and 2 isothermal processes. Okay, you can see we have difficulties, okay, when we use the Carnot cycle with the steam as follow here. The first reason why it's not that good or it's very difficult to use Carnot cycle is in the process 1-2. Process 1-2, you can see we pump the vapor liquid mixture from number 1 to the set liquid number 2 here. Okay, but the equipment that we use to increase the pressure here, we use the pump. The pump can be used or designed to increase the pressure if the working fluid is only liquid. It cannot be used to increase the pressure of the vapor. So it's not practical to design a pump which can handle two phases between vapor and liquid here. So this is the first reason why Carnot didn't work well with the vapor working fluid. The second reason is that in the heat addition process in the boiler, which is an isothermal process, we will have a temperature at number 3. Normally, we want to make the steam here to be superheated steam to take advantage of higher temperature. Okay, take advantage of the superheated steam to generate more work. So we actually would like to change from saturated vapor into the superheated steam. But if we do it in an isothermal way, it means that to maintain the temperature, you have to decrease the pressure. Maintain temperature. Pressure must be decreased. Pressure must be decreased. So it's rather difficult to construct a boiler which can expand or inflate it, okay, or decrease the pressure, as you want to maintain the constant temperature along the process here. It's very difficult. So it's actually not practical to construct the boiler which can inflate to a bigger volume when you add heat in. Okay, so this is not good. Okay, not practical. And the last reason why we cannot use Carnot with the vapor is that when you expand the steam in the turbine from point 3 to point 4, you can see that the steam will be at a lower quality. At number 4 here, you can see that you have some liquid formation. Some liquid formation. And this is not good for the turbine blade, because turbines spin at a very high velocity. If you have liquid formation, the liquid droplet, which is the incompressible liquid, will move at the same velocity as well. So when it spins at a very high velocity, liquid can impinge or it can hit the impeller blade or turbine blade, and it can damage the turbine blade during the expansion. So this is not acceptable in practice as well. Okay, so in practice we must limit the amount of liquid formation in the turbine. Okay, normally we want it to be less than about 15% liquid formation. Okay, so less than 15%, okay, liquid is the practical value. Less than 15%. Okay, so you can see with these 3 reasons we cannot use Carnot vapor cycle with the vapor or steam. So to resolve the difficulties associated with the Carnot cycle, the Rankine cycle was devised. So we will create the Rankine cycle instead. And in this slide, the explanation that I have just explained previously. Now, the ideal Rankine cycle. The simple ideal Rankine cycle has the same component layout as the Carnot cycle shown before. Okay, but instead of isothermal process, it would be replaced with isobaric process in the heat addition and in the heat rejection process. So let me explain step by step about the details of the ideal Rankine cycle on the TS diagram here. Now, to avoid pumping to a vapor and liquid mixture, okay, avoid pumping vapor liquid mixture, we have to pump it in the liquid phase. So we have to make sure that point number 1 is at least on the saturated liquid line, okay. And if I say ideal Rankine cycle, it means that number 1 would have to be sat liquid. Sat liquid here. Okay. So the first process would be process 1, 2. Start by pumping the sat liquid, okay, to a higher pressure. So we have two pressure here, P high and P low. Okay. Pumping the liquid from sat liquid into the compressed liquid. Number 2 here would be compressed liquid or subcooled liquid. Compressed or subcooled liquid. Okay, and after that the subcooled liquid will enter the boiler where it has a temperature change to the sat liquid and undergoes phase change to sat vapor, and then has a temperature change to the superheated vapor at number 3. Okay, so process 2, 3, you can see that it involves the sensible heat of the liquid in the first part, latent heat in the second part, and the sensible heat of the vapor to the superheated vapor in the last part. Okay, we have Q in this part, in this process here. All occur on the same constant pressure line. Okay, 2, 3 occur on the constant pressure line here. The next step would be isentropic expansion. Isentropic expansion from number 3 to number 4. Okay, so the exit from the turbine, it may be in the vapor phase region or still superheat, or it may enter the two-phase region, or we have some liquid formation at number 4. It depends on the original point or the inlet point from the turbine. Okay, and after that, from number 4, the sat vapor here or vapor liquid mixture here will be condensed into the sat liquid at number 1 again. So this is the basic description of the ideal Rankine cycle. Okay. Right then, now let's take a look at a simple calculation example of the ideal Rankine cycle. Now in this example, we want to determine the thermal efficiency of an ideal Rankine cycle. Need that thermal here. Okay. The condition is that the steam leaves the boiler as the superheated vapor at 6 megapascal, 360 degrees Celsius. So this is P3 and this is T3. Okay, at the outlet from the boiler here is number 3. And is condensed at 10 kilopascal. So this is P4, which is equal to P1 at 10 kilopascal. Okay, so if we draw the Rankine cycle on the TS diagram, you have a shape of the cycle on this red cycle here. Okay, 1, 2, 3, and 4. Okay, it operates between two pressure values, 6,000 kilopascal or 6 megapascal and 10 kilopascal. Now, because this Rankine cycle is ideal, so it means that point number 1 would have to be sat liquid. So we have point number 1 here on the saturation line. Okay, on the sat liquid line. This is point number 1. Okay. So if you look at the diagram, you can see that we have some point that is fully defined. Fully defined means that you have two pieces of information, and the other properties, for example, enthalpy, the temperature or pressure, can be determined. Okay. Let's have a look at the first point, point number 1. Point number 1 here, you know P1. P1 equal to 10 kilopascal. And you also know that at point number 1, it is sat liquid. So it means that you have two pieces of information now. In this case, you can go to the sat steam table to look for other properties. Look for the enthalpy values. Okay. Look for the temperature, the sat temperature value as well. So number 1 is fully defined. Similarly, on point number 3. On point number 3, you know T3 equal to 350 degrees Celsius. And you know that pressure P3 equal to 6,000 kilopascal. You also know two pieces of information as well. You can use the superheated steam table to look for other properties. Number 3 is also fully defined. Okay. So in this case, you are left with point number 2 and point number 4. Point 2 and point 4 are not fully defined. Okay. Point 2, you know only the pressure. Point 2, you know only the pressure. Okay, which is 6,000 kilopascal. Okay, and point 4 as well, you know only the pressure, which is 10 kilopascal. Okay, so you have to determine the other properties for point number 2 and point number 4 to make it fully defined, and you can calculate all the properties related at that point. Okay. Now, to start our calculation, let's consider each process one by one. We can start with pump. Okay, pump is process 1, 2. Okay, we can do the material and energy balance in this process. From the material and energy balance, you can have this equation. The work required for your pump would be equal to m dot multiplied by H2 minus H1. Now, since number 1 is fully defined, you can then determine enthalpy at point number 1. Okay. But at point number 2, you know only the pressure. Okay, so point number 2 is not fully defined yet. And at point number 2, it would be in the compressed liquid region. In the compressed liquid region. So if you want to determine the enthalpy, you normally need the compressed liquid table or the subcool table. Okay, which is normally unavailable. Now in this case, we will use a second method to determine the pump work instead of calculating from the enthalpy change across the pump. Okay, we will use a second method to find the pump work instead of using enthalpy change across the pump. We will use the thermodynamics property relation dH equal to TdS plus VdP. For the pumping process here is isentropic. So we will have no entropy generation, ds equal to 0. So the first term becomes 0. So we have only dH equal to V multiplied by dP. So if we integrate, okay, on both sides from inlet to the outlet of the pump from point 1 to point 2, you will have enthalpy change H2 minus H1 equal to integral of V dP from point 1 to point 2. Now, Normally the specific volume here would be changed if your working fluid is gas. But in our case, it's a pumping fluid. It's a pumping of the fluid which is incompressible. Incompressible fluid. Liquid is incompressible fluid. So it means that the specific volume will not change that much. We can assume that the specific volume would be constant at the inlet point. The specific volume at the inlet point, we can determine that value easily because V1 would be at sat liquid. Okay, at sat liquid. So we can use the steam table to determine V1. So if our specific volume here is constant, you can take it out from the integral term, and the result would be just H2 minus H1 can be approximate as V1 multiplied by P2 minus P1. So in this case, you can calculate the pump work from the pressure change from the inlet to the outlet directly. Pump work will be equal to V1 multiplied by P2 minus P1. Now, from the steam table, at point number 1, P1 equal to 10 kilopascal and sat liquid, you have enthalpy, sat liquid enthalpy, HF, at 191.81 kilojoule per kilogram. You have the specific volume of the sat liquid at 0.00101 cubic meter per kilogram. So you can use the approximate equation that we have just developed here to calculate the pump work. So the pump work will be equal to 6.05 kilojoule per kilogram. Okay. Now in this case, we have a conversion factor here. This is an important conversion factor, which is 1 kilojoule per cubic meter equal to 1 kilopascal. Okay. So if you want to use this conversion factor, you have to make sure that the unit of the pressure would have to be in kilopascal. Unit of the specific volume would have to be in cubic meter per kilogram. So you can use this simple conversion factor. If you use a pressure in the other unit, the result, you have to look at the result in a very careful manner. Okay. So you have the pumping work. Now, once you have the pumping work, you can go back to your material and energy balance equation that you have developed earlier to calculate the enthalpy at the pumping outlet, or H2. H2 here can be calculated from W pump plus H1. So H2 would be 197.86 kilojoule per kilogram. Okay. So point number 2 will become fully defined now, because you know the enthalpy at this point. Okay. Now once we know the condition at number 2, we can move on to the boiler, which is process 2-3. Process 2-3. Similarly, we can start with the material and energy balance. Okay, so you have the Q in equal to m dot multiplied by H3 minus H2. This is the material result from the material and energy balance in the boiler. Okay, the properties at state 3 can be determined from the superheated steam table. So at P3 equal to 6000 kilopascal, temperature at 350 degrees Celsius, you can get enthalpy at that point and entropy at that point as well. You can then substitute H3 into your energy balance equation. You can calculate Q in, or heat transfer per unit mass, in your boiler, and that would be 2,845.1 kilojoule per kilogram. Okay, now let's move on to the next step, the turbine, which is process 3-4. In process 3-4, we can also do material energy balance to get this equation. W turbine equal to m dot multiplied by H3 minus H4. Okay. Now you know that point number 3, you already know the enthalpy values. Okay. And point number 4 here, you don't know the enthalpy value. But at point number 4, you know P4 equal to 10 kilopascal. And you know that in process 3-4 is isentropic. So S4 will be equal to S3 equal to 6.3357 kilojoule per kilogram Kelvin. So it means that you now know two pieces of information now, pressure and entropy. You can then use the steam table to determine the other property values. Now in this case, we have to check at point number 4 whether that point would be in the vapor phase region or in the two-phase region. We can compare the entropy value at point number 4 with the entropy value of that liquid and entropy value of that vapor at 10 kilopascal. So we take the value of SF and SG at 10 kilopascal from steam table, okay, from the SAT steam table, and then we compare our S4 with this SF and SG. If our S4 is less than SF, it means that point 4 would be subcool liquid. If S4 is greater than SF but less than SG, it means point 4 is in the mixed phase region. And lastly, if S4 is greater than SG, it means that point number 4 would be in the superheated vapor. Okay, superheated vapor region. Now you can see from the number that we have, S4 is 6.3357. It lies between SF and SG. So it means that point number 4 is in the mixed phase region. This one. Okay. Now, since it's in the mixed phase region, the property would have to be the weight average properties between the vapor portion and the liquid portions. So you have to determine the vapor fraction or the liquid fraction first. Okay, you can determine the vapor fraction by using this equation that I have shown here. Or you can use just the mixture property equal to the weight fraction of the vapor and the liquid properties. Okay, so S4 equal to 1 minus X4 multiplied by SF plus X4 multiplied by SG. Okay, if you rearrange this equation, you will have X4 will be equal to S4 minus SF divided by SG minus SF. Okay, SG minus SF would be SFG that you can get directly from the steam table. Okay, so at point 4 here, once you substitute the entropy value at point number 4, entropy value of the sat liquid entropy value of the sat vapor, you have the vapor fraction of 0.758. This is the vapor fraction. You can then use the same concept to determine the enthalpy of the mixture. Enthalpy of the mixture would be calculated from the weight average properties. H4 equal to 1 minus X4 HF plus X4 multiplied by Hg. Or you can use this equation, H4 equal to HF plus X4 multiplied by the latent heat, HFG here. They are similar. Okay, they are both similar. Now, you have HF and Hg from the steam table. Okay, HF and Hg, okay, you get from the steam table at 10 kilopascal. Okay, so you can calculate H4 now. H4 would be 2005 kilojoule per kilogram. Once you know the enthalpy at both inlet and outlet, you can calculate the turbine work, okay, from the energy balance that we have developed previously. W turbine would be 1038.9 kilojoule per kilogram. Now we have complete the energy balance in all processes, in the pumping process, in the boiler process, and in the turbine process. You can then calculate the net work done by the cycle. W net would be W turbine minus W pump. So W net out would be 1032.8 kilojoule per kilogram. And you can calculate the thermal efficiency now. Thermal efficiency would be W net divided by Q in that you have previously. The thermal efficiency is 0.363 or 36.3%. So this is the result of the efficiency of this ideal Rankine cycle. Okay, so you can see that the way we work in the calculation of the Rankine cycle will involve the use of steam table. Okay, so you have to be very clear, okay, about how to use the steam table in order to solve these problems effectively. Now, there are also several ways to improve the simple Rankine cycle efficiency. The first way is that we can increase the cycle efficiency by put the vapor into a higher superheat level. Okay, so in this case, if you increase the superheated level from 3 to 3 prime, okay, you can see that the average temperature during the heat addition will be higher. Okay, you have a higher potential to generate work from the turbine. Okay, and the benefit that you also get would be the reduction of the moisture content, the reduction of the liquid formation at the turbine outlet will be decreased as well. Okay, and the typical value, we want the vapor fraction to be greater than 85%, or the liquid formation would be less than 15%. This is the practical value that we normally require. So you can see that here you have increase in the area, which is the pink area here. Increase in the area means increase in W net. So this is a simple way that you can increase or improve the cycle efficiency by increasing the temperature of the superheated vapor. The second way is that you can also increase the boiler pressure. If you fix the same you fix the process at the same maximum temperature but only increase the boiler pressure. You can see that if you increase the boiler pressure, you have more area from the pink area here. It means that you get the more network output. Okay, but if you operate at the same maximum temperature, it means that you have to expand into deeper into the two-phase region. Okay, so you can see that when you compare with the original cycle here, you have the gray area, which is the decrease in W net. Gray area here represent the decrease in W net. And the disadvantage that you get in this choice would be you also produce more moisture at the turbine exit as well. Okay, because X4 prime is less than X4. It means that we have more liquid formation at the turbine exit. Which is not good. Okay, so you can see that for this choice, if you increase only the boiler pressure while keeping the maximum temperature constant, it's not seems to be a very good idea. You cannot evaluate whether you have better benefit from the increased area or not, because you have more area on the pink zone here and you have less area on the gray zone here. And you also another disadvantage from the more liquid formation as well. So it's not clear cut whether we have the actual benefit by this modification or not. The next one. The next way to improve the Rankine cycle efficiency is by lowering the condenser pressure. If you lower the condenser pressure, you can see that when compared to the original cycle, you have more area in the pink zone here. Okay, this is the benefit that you get. It means that you reduce the energy loss to the surrounding. You will have less energy loss to the surrounding. Okay, but the disadvantage is that the turbine exit here will have more liquid formation. X4 prime will be less than X4. Okay, or it means that you have more liquid at the turbine outlet. Okay, so when we look at all the way that we have considered here, increase the superheated vapor temperature, increase the boiler pressure, or lowering the condenser pressure, we normally don't choose one of them, only one of them. We may have to combine every approach, okay, to improve the Rankine cycle efficiency. We may have to do them all. Increase the superheated temperature, increase the boiler pressure, reducing the condenser pressure. We may have to do all. We may have to do all of them. Okay, we may have to do all of them. Now, there is also another way to improve the Rankine cycle efficiency. In this way, we will make use of the supercritical pressure. Supercritical pressure in order to increase the cycle efficiency. In the supercritical cycle, it means that what happened in the boiler will be in the supercritical region. What happened in the boiler here will be in the supercritical region. It means that the pressure in the boiler and the temperature in the boiler would be very high. Okay, so you can see that instead of going through the phase change across the phase boundary from sat liquid to sat vapor, you actually pump your water to the supercritical pressure, and then heat it up. Okay, heat it up. So your supercritical fluid will go over your phase boundary, go over the steam dome. Okay, so in this kind of cycle, this kind of supercritical cycle, the efficiency would be very high, but the investment would be very high as well. Investment would be very high because you have to operate at very high pressure and temperature. The material that you use to construct your boiler would be a very expensive material. It must be kind of special alloy which can handle high pressure and high temperatures. Okay, at the present we don't have the supercritical steam power plant in Thailand. We don't have one, but in the US there are more than 150 supercritical pressure steam power plant in operation now. Okay, so this technology is widely used in the US but not in our country. Okay, and that should be all for this part. See you in the next part.